DF discrete time Fourier transform if I take, so it was like something x of e power j omega was summation n is equal to minus infinite to infinite x of n times e power minus j omega n, right? And if I want to find out x of n, which is like, is an x of n? Yeah, it's 1 over t with the integral minus pi to pi in the DTF x of e power j omega times e power j omega, right? So if you observe the Fourier transform, so this was the DTFT. If I take DFT, right, discrete Fourier transform, right? In this case, we just found the XR was summation n is equal to 0 to n naught minus 1, right? X of n e power minus j r omega naught n. So if you observe, it is exactly the same, right? Except this was in the discrete Fourier transform. Clear? So if you observe, it is exactly the same formula. And if I take the Z transform, if you clearly observe the Z transform, so you can have the relationship between DTFT, DFT and Z transform. So if I consider the Z transform, which will be discussed in like chapter number 5 or something, so x of Z, if I consider the x of Z, this is nothing but still summation n is equal to minus infinite to infinite x of n times Z power minus n. So this is the definition for Z transform, right? So if you compare, if you clearly observe, Z is nothing but e power minus j omega, right? If you compare the Z transform or DTFT, it is nothing but e power minus j omega, right? So if I go with the continuous Fourier, that was discrete time Fourier transform, right? If I go with the continuous Fourier transform, if I want to go with the continuous Fourier transform, it is still the exactly, which is like which is summation n is equal to minus infinite x of n e power minus j omega n. So x of n, whereas in the inverse, so this is the inverse DTFT, right? So this was the DTFT and this was the inverse DTFT and this was the DFT, right? The Z transform. You can see the relationship, how they have been changed. You can see that they have exactly the same stuff, but only when I'm considering the Z transform, the e power minus j omega will be Z, right? In the same manner, this will be e power minus r omega naught, right? We know that, which is nothing but 2 pi over n naught. Is that clear? So these are the relationship of DTFT, DFT and Z transform. And the continuous also is same, like something e power minus infinite x of 1 over t, I guess. 1 over t x of the continuous signal, which is x of capital T power j omega t. Continuous, because I'm taking continuous, not the difference. So this is something, I remember that was the form, right? So it was DTFT and DFT. Let's see, you can observe like what all you can see the change. So you can see still everything is exactly looking same, right? So but only Z is nothing but e power minus j omega. In the same manner, in this case, omega is nothing but omega naught times t, right? Omega naught times t. That's what it is. It's clear with this relationship. So these are the relationships for 3 transforms. We'll be discussing this one as soon as we are done with this chapter. with Z or with this. So these relationships are very important. Maybe if you go for like higher studies or something. So sometimes you don't want to go. So sometimes you'll be confused like what's happening with discrete or what's happening with discrete time or discrete Fourier transform or Z transform or continuous Fourier transform. So this is the only stuff you have to analyze them in order to analyze it, right? Let us take one example, like 8.7. Still have 5 more minutes. So here, 8.7, a signal x of t has a duration of 2 milliseconds. The x of t has a duration of 2 milliseconds and an essential bandwidth of B is 10 kilohertz, right? So here the goal is a frequency resolution of 100 hertz in the DFT and determine N naught. We know that N naught is T naught over T, right? And or else you can make it as Fs over F, right? Fs over F. And here, the signal duration which is given in the time domain. So in this case, I have like something with bandwidth is like 10 kilohertz, right? I have this bandwidth of 10 kilohertz, and here I have a frequency resolution. The frequency resolution is of 100 hertz, right? So in this case, the frequency resolution is nothing but f naught, which is like 100 hertz. Therefore, I can find out t naught, which is 1 over f naught, which is like 0.01 second, right? And but if you observe, the signal x of t has a duration of only 2 milliseconds, right? But we have almost 10 milliseconds. The total was like something t naught was 10 milliseconds, right? This was. But we have the signal duration was at only 2 milliseconds, right? Therefore, it is like 10 milliseconds minus 2 milliseconds, which is like 8 milliseconds, right? So that's the signal duration. I mean, that is like zero padding of 10 milliseconds minus 2 milliseconds, which is like something around 8 milliseconds, right? I have the bandwidth. So for finding Fs, Fs is nothing but we know Fs is 2 times of B, right? So we know it is 2 times of 10 kilohertz, right? Which is 20 kilohertz, right? I have Fs, I have T, right? I have T naught. This is my T naught, and this is my Fs, right? Or zero padding, which is N naught, or Ts is nothing but 1 over Fs, right? It is 1 over 20 kilohertz. 100, that gives me my value for n, which is something around 200 samples. So if you observe, I have zero padding, which is like something 8 milliseconds, right? So it is like 2 power n naught will be something like 256, which is like 2 power. Since we have a power of 2, which is convenient for the 50, to choose n naught with 256. 256. Now, reducing the aliasing error. So if I take, now, increasing n naught has 2 benefits. If I increase my value for n naught, which gives me 2 benefits. First one, reducing the aliasing error, right? So I can reduce my aliasing error, that is the less trial overlap, right? So you can see that in this figure, I made with the 3 different colors, where you can see that there is a less trial overlap. That is, I'm reducing the aliasing error, right? So by increasing n naught, right? First one. So I know that my new n naught with the increase n naught was 256, right? So this was 200, but my n naught was 256, right? That's a new n naught, right? So the new sampling frequency will be, so the fs double prime is nothing but, it's a new sampling, right? First case. So which is n naught, since we know that n naught times f naught, right? So the new n naught is like something 256 and like f naught is like 100 hertz, right? Which is 25.6 kilohertz. Do you have any questions? So the first case, reducing the aliasing error, right? So if I increase the n naught, since I know that from this I found the n naught was something around 200 samples, right? So I can find it as 2 power 8, which is like at 2 milliseconds, it is like 2 power 8 samples, right? Which is like 256 samples, right? So in this case, 200 and 256, like I'm increasing the value for n naught. If I increase the value for n naught, therefore I'm reducing the aliasing effect, right? The aliasing error. That is, you can see that it is like less, there is a less trial, you can see that there is a less trial overlap in this, right? So if you observe, there is a less trial overlap in that, which reduces the aliasing, so which is like something 25.6. Right? And now, and I can find out new T, which is 1 over Fs, new sampling time, which is 1 over F dash, which is 1 over 25.6 kilo, right? Which is something. And the next one is the improving resolution. I can improve the resolution, right? So which is, I can find out with the new F naught. First one, that's by using the sampling. Since, remember, if I have the signal, if I have like x of t, that gives me something x of omega, right? And if I have like something, I have like x of omega, x sampling of omega, right? Which has something, the aliasing in it. Right? So in this case, if you observe, by increasing n naught, I'm reducing this aliasing effect, right? And by increasing n naught, I can increase the resolution of this x omega, right? I can increase the resolution of the original system x omega, right? Here, so which is like resolution, which is like T naught is nothing but Fs over F naught, right? So F, I need to find out by increasing it, I can increase the resolution, which is F naught. F naught is N naught over N. The N naught is like 256, the new N naught is like something 256, right? And Fs is 50, like, which is 1 over something like this. 20 hertz, right? Which is something 256 over 20 kilohertz. That gives me the value for F. No, that gives me the value for F. So you can see that, which is around, so the F naught is around 78.12. So this was around 39 and this is around 78.125. So if you clearly observe the values of F naught, the given value was 100 hertz, right? So the new value for F naught was something 78.12, right? So therefore the frequency resolution is improved from 100 hertz to 78 hertz, right? So by increasing N naught, the given value was 100, right? So by increasing the N naught to 256, so which is like, it got like better, right? Which is like 78, right? So from here, you know that I'm improving the resolution, right? In the same manner, here I have Fs. Fs was like something around 20 kilohertz, or Fs was 20 kilohertz, and in this case Fs was 25.61 kilohertz, right? In order to reduce, I already mentioned one important point. In order to reduce the aliasing, right, I need to increase the Fs value, right? So in order to reduce this aliasing, I need to increase the Fs value. So if you clearly observe, my Fs value has been increased, right? That indicates I'm reducing the aliasing. Clear? So if I have a sample has a frequency resolution, right? And I know that I found the N naught, which is like something like 200 samples, right? But I know the new N naught is like 256, right? By using this new N naught, I can find out the new resolution, new frequency resolution, and the sampling frequency Fs, right? So I can find this two. So by increasing the Fs, I can reduce the aliasing, right? By increasing the if my F naught is decreased, that is nothing but I have good resolution. That is like I'm increasing the resolution of that signal, right? And there is a combination, like you can choose T is like 45 microseconds, and that gives you something like 22.5 kilohertz, right? So which has F naught as 86.8 hertz, right? So which is again decreased from 100 to 86.8, right? Let us take few more examples in the next class, and we'll start the chapter number 3 after your midterm. And I'll post the midterm question paper today after I go to the office.